Now, I would like to call upon the last presenters, two presenters, Mr. Chirayu Shah, Team Lead Thermodynamic Calculations, Siemens Limited, and Mr. Viraj Pawar, Senior Manager Sales and Marketing of Siemens Limited. Viraj Pawar. Chirayu. Viraj Pawar. Okay. This is brief resumes of both. Mr. Chirayu Shah, presently a thermodynamic calculations team lead for steam turbine sales and proposal. 13 years he has got experience in thermodynamic calculations for steam turbines. And Mr. Viraj Pawar, working as senior manager sales in Siemens Limited, steam turbine and generator division, responsible for West region sales and EPC business. Viraj is experienced sales professional with a demonstrated history of working in the power, oil and gas sector and is skilled in consultative sales proposal, engineering, commercial out contract negotiations and business development. Please carry on your presentation.
Good afternoon all. Good afternoon all. First of all, thank you dignitaries for having us over. I am Viraj Pawar from Steam Turbines Division of Siemens Limited. And along with me, we have a sales colleague of mine, Mr. Lalit Sarunke and Mr. Chirayu Shah, who is the team lead for thermodynamics calculation in Steam Turbines Division in Siemens India. So we are basically a steam turbine manufacturing company globally, and we belong with an Indian manufacturing facility. We have our headquarters in Vadodara. So it is not just our friends who presented earlier, they are Indian company, but also we do manufacture steam turbines in India and we also export. So our range starts from 100 kilowatts and we go right up to 250 megawatt from our Indian facility. So topic for today, although the main topic for this seminar was heat and mass balance diagram for a complete sugar plant, the subtopic which was allocated to us was thermodynamics with respect to the steam turbine. So without much wasting time on introduction of Siemens, I would pass on the dais to Mr. Chirayu Shah to take on, dive in right into the main topic.
Good afternoon. Thank you for thank you for this opportunity. So in this whole sugar plant, what we are now going to talk about is this particular cogeneration plant, which is a part of complete sugar plant. So what is best for this sugar cogeneration plant is it has the inherent fuel, which is the byproduct of the process plant, which is already available in because for many other plant the fuel is coal or any other fuel need to be arranged for the electricity generation or the process steam generation. But for sugar plant, it is very inherent benefit is that the fuel is the byproduct of the process, and there is a requirement of electricity in the sugar mills, and also there is a requirement of steam in evaporator and other processes. So all these three combined encourage the cogeneration plant in the sugar plant. So basically in this cogeneration plant, the bagasse from the sugar plant is fed to the boiler, and also the condensate water is also given to the boiler, and due to the heat from the bagasse in the boiler, this water is going to be converted into high pressure steam. This high pressure steam rotates the steam turbines, and then subsequently this steam turbine generate the electricity through the generator. Now this electricity major part of will be consumed by the sugar plant itself, and surplus electricity can be exported to the grid as per the agreement of individual sugar plant. And also the low pressure steam is taken out from the steam turbine, which is again fed to the sugar plant. And if it is the condensing turbine, then there will be also the condensate coming from the turbine exhaust, which is through pump again went to the deaerator or feed water tank, whatever setup is there. So now as we are going to talk about the heat and mass balance of the cogeneration plant. Before that, it is very much important to go through the thermodynamics of the heat and mass balance of the cogeneration plant, which is basic ideal Rankine cycle, because our ultimate aim through heat and mass balance will be to optimize the cogeneration plant efficiency as much as possible, and which is also the need of an hour. So to optimize the complete heat and mass balance diagram, we just need to go to some basics and identify the areas where we can improve the efficiencies. So the first is 1 to 2, where the compression is done in the pump where the water pressure is increased, and that high pressure water is gone to the boiler. In boiler, from 2 to 3, sensible heat, latent heat, and again sensible heat is given to produce the superheated steam. This superheated steam is expanded in the turbine and convert this rotational mechanical power, and that will be further converted into the electricity, and the heat rejected from the turbine is going to the condenser, and from condenser again the um, uh, latent heat is synced, and again steam is converted into the water. Now the thermal efficiency of ideal Rankine cycle. So the 2 to 3, the whole area below this 2 to 3 is the total heat added in the cycle, and the and the 1 to 4, below 1 to 4 is heat rejected from the cycle. So whatever the area between purple line is ultimately it is our work done. So efficiency of the ideal Rankine cycle is what is the total net work. Means there is some work generated by the turbine and also some work consumed by the pump. So whatever the net work is there and whatever the total heat is supplied is ultimately the thermal efficiency of ideal Rankine cycle. Now how can we improve the Rankine cycle? So if we see in this Rankine cycle, if we lower the condenser pressure, then the area in the Rankine cycle can be increased. So because of that we can improve the efficiency of Rankine cycle. Again, we can superheat the steam to the more temperature, and by that the Rankine cycle efficiency can be increased because the power generation can be increased. We can also increase the boiler pressure. So on the other side, by increasing boiler pressure, the left side power will be slightly reduced, because the Rankine cycle is shifting towards the left, but the top side we are going up, so that additional power will be there. But by increasing the boiler pressure, there will be limitation of the moisture level at the turbine exhaust, because we are going towards left in the Rankine cycle, so moisture at the turbine exhaust is going to be increased. The other two is basically the upgradation of Rankine cycle, which is regenerative cycle, where the feed water heating is used to effectively lower the means increase the average temperature of heat addition. So because of that, the less heat need to be added in the boiler. Another is the reheat cycle. So reheat cycle is mainly more useful for the higher pressure cycle, so that when the moisture level at the turbine exhaust is going to be increased, we can again reheat the steam, so that the turbine exhaust at the end of the final turbine exhaust, the moisture level is not too high. Now this is the typical isentropic heat drop in the steam turbine. We are not just going detail in it, because just the means basic message from this is that with the increasing the steam parameter, the overall useful energy is increasing, and because of that the overall cycle efficiency can be increased by the increase of the steam parameter. Now the major losses in Rankine cycle which we have to reduce to overall improve the Rankine cycle efficiency and improve the efficiency of overall heat and mass balance diagram. So there are some pressure losses in the boiler, heat losses in the boiler, also the piping losses from boiler to steam turbine. Then there will be some irreversibility in the steam turbine. There will be some losses and irreversibility in the pump. There will be the heat losses and also the mass losses in the cycle. and there will be some subcooling at the condenser outlet and the pressure drop. So all these things we can target to optimize the efficiency. Being a steam turbine manufacturer, our main aim is to improve the turbine efficiency as much as possible. Because of that, the efficiency of complete cogeneration plant can be increased. So ultimately, what is the isentropic efficiency of the turbine? So the isentropic efficiency is that with the ratio of the actual turbine work, means the heat energy converted to the work divided by what is the maximum heat energy that can be converted to the work, keeping the entropy constant. So that is ideal, that is isentropic process, which cannot be occur. There will be some irreversibility, and because of that the entropy is going to increase and the actual turbine work is going to be less than the isentropic turbine work. So now there is some basic of I am just going fast for this slide because it is already explained earlier. So there are main things in the turbine for the efficiency is the blades, and this is how the blade works, where the because of the conservation of momentum principle, the heat energy is finally converted into the kinetic energy and the shaft power. Now there are basically two type of blading: impulse blading and the reaction blading. So the impulse blading has I'm going to fast with this impulse blading and reaction blading. So reaction blading is more efficient for some of the range, and because here the aerodynamic losses of the profile can be reduced in the reaction blades compared to the impulse blade, and also the pressure drop is occurred in the both the stationary and rotating part of the blading. So now basic philosophical difference. So if you see here the rotating blade, upside is the impulse and the lower side is the reaction. So upside is the more or less the bucket type construction, and the lower the in reaction blade there is a aerofoil construction. So this is the velocity drop and the pressure drop inside the blading. So in impulse the all pressure drop is occurred in the stationary blade, whereas the in reaction both stationary and rotating blade has the pressure drop. And here the basic difference between the impulse and reaction, where the in impulse blading there is higher aerodynamic losses in the blading, and also there is a high energy conversion rate per stage, and the stator design is also somewhat complicated and at the higher cost, whereas in reaction turbine the velocity the losses of blade losses, aerodynamic losses are lower. There are symmetric blading. There is high thrust because of the blading pressure drop, but it can be compensated to the balance piston. So there will be some leakage loss in the dummy balance piston, so that thrust has been accounted, and the lower complexity of blading. Now how can we further improve the efficiency of steam turbine? Because this is the very much need of an aware to further keep on the first of all we have to find the where are the losses in the steam turbine, so that we can do the R&D to reduce those losses. So losses basically are the profile losses because of the wall friction losses, because there will be the layer of the steam on the blades, and because of that layer, boundary layers, there will be the friction losses. There are trailing ledge losses, and there are incidence losses when the steam is incident to the blades. There will be secondary losses as hub and tip counters. There will be leakage losses as shown in the diagram, because there will be some radial and axial clearances in the turbine. Because of that, the rotating and stationary part do not collide with each other, so there will be some clearances. So there will be leakage through that, and there are some additional losses because of the angle loss or the windage loss. So now over the period of the time, the blade design is continuously developed to improve the efficiency of the steam turbine. So first was there was the in reaction blade there was the cylindrical blade, where the cross section throughout the blade is constant. Now then, the first generation of advanced 3D blade was come where the where the cross section from hub to tip is changing to optimize the efficiency, and then there is a further research is going on, and now we do have the 3D third generation advanced 3D blading, and because of which we can improve the steam turbine efficiency further. Now this is the typical heat and mass balance diagram where you can see the steam turbine. So the water is coming from this boiler to the steam turbine. This is for the extraction condensing turbine, where one blade is taken for the distillery and the internally controlled extraction is for sugar process. There is gearbox, so the turbine is high speed turbine, so between turbine and generator there is a gearbox for speed reduction. There is a air cooled condenser, there is a condenser extraction pump, this is ejector condenser, the steam jet ejector which maintain the vacuum inside the condenser, and we are also utilizing that heat in the ejector condenser. There is a derator in the cycle for deration of the removal of the air. Then there is the boiler feed pump, and there are the HP heaters if there are any. Now in back pressure turbine, what are the major parameters which can affect the power generation? So first is that the inlet steam parameter, which is the pressure and temperature. Then the back pressure at turbine flange, because at sometimes some sugar plant required 1.1 kg per cm square gauge at plant, some required 1.5 kg per cm square gauge at the sugar process. So as this pressure is going to be reduced, you will have the less pressure drop in the turbine, so that the back pressure affect the power generation. Then the process flow, distillery flow, process return condensate, how much condensate water is been recovered from the process and coming back to the cycle, that is also very much important. And the feed water temperature and other. This is typical the specific steam consumption. We just depicted that the with increase of steam parameter the steam consumption is reducing. So this is one case study for 5000 TCD plant where we have made some assumption that the steam required is 40. So with that 90 TPH process is required. If the as we understood that now we also have the plants with 30% sugar process, so it will reduce to 70 TPH. So it will only change our figure, but whatever the conclusion is that the trend will remain same. So here is the sum of some trends. Here there is first three cases are with the 110 540 boiler steam parameter, means at turbine inlet we have considered 105 535. There are three cases with 88 520 boiler steam parameters and two cases with 67 485 parameters, and we have considered the different feed water temperature. So these are the regenerative cycle, and here there is only derator, and this is the boiler steam generation approximately based on our considered 90 TPH process steam flow. So we back calculated the inlet steam flow required to maintain the process steam flow and the feed water heating, and based on that this is the power generation, and this is the heat added in the steam side in the boiler based on the final feed water temperature and the steam parameter, and this is the heat required in the boiler based on the assumption of 70% Baga's best boiler efficiency, and based on that we calculated the Baga's required with the assumption of 2050 kilocal per kg gross calorific value. So if you see the by feed water heating, the Baga's consumption is going to be increasing with the feed water heating because we are generating more steam. But on the other hand, the power generation is also increasing. So if we see in this slide that this first three is with the sequence is the same, means the first is with 2 HP heater, 1 HP heater and without HP heater. The sequence is the same here, and here you can see the Baga's saving per hour based on the different configuration, and on the other end the power exports. So here the Baga's saving is less, but the export power is higher. So based on the overall phenomena at the sugar plant, how they are storing the bagas and how they are going to use it in the off season or any other process, or what is their power export commercialization. Based on those aspects, decision can be made that bagas savings should be more preferable or the power export more is preferable, and based on that the parameter and cycle configuration can be selected. Now for condensing, this trend will be typically same, but we didn't depicted here because for condensing in during season case, anyhow the bagas saving is going to be reduced and the power generation will be increased. Trend will be same because we are going to send only 10% steam to the condenser and that steam is going to be increased. But overall trend with respect to parameter and the feed water heating is going to be same. And these are the major parameters affecting for the extraction condensing turbine. Here the major two additional will be the what will be the condenser type, whether it is will be water cooled condenser or air cooled condenser. That will also affect the power generation because with okay, and also the off season case maximum power generation will affect the turbine design and power generation. Thank you.
Now house is open for interactions.
Yes, sir.
Typically, what kind of efficiency drops have you seen over a period of 1 year? 1 year. Sir, 1 year is too short period. IEC defines the efficiency drop for a period of over 10 years. So 10 years के लिए we have seen
Mic ऐकू येऊ दे.
So the question was, what are the efficiency drop that we envisage for a period of 1 year, right? That was the question. So 1 year is a too short period unless and until you are not maintaining the water quality very correctly. So IC states that about 7% of efficiency drop can happen over a period of 10 years time. But again, that depends on OEM to OEM and what is the quality of material that they're using for the rotating and the stationary part. But yeah, that is the limit that has been set by IC. That is an anticipated limit. Again, as per our experience, so since we are dealing mostly into reaction technology, the efficiency drop that we are seeing for period of 10 years is about 2%, less than 1.5 to 2%. That is the range that we look after. So that is your question is valid, sir. But I would urge you to use one of our Siemens steam turbine. In that you will see whatever we guarantee on paper is the actual figure that we have.
No, Siemens is not the case. General.
Generic. So ideally, if the turbine is designed correctly, and if the sales team has presented the client the facts correctly, ideally whatever is there on HMBD should be the PG case. Ideally. Any more questions?
Okay, fine.
In my view, there is no steam the efficiency loss because if the turbine material and the input of the turbine is all right, then even years together, even for decades, it is not going to have any year efficiency loss. Because I have seen in the year 1933 turbine was installed and that brown Bowry turbine worked up to till now it was working, and with very good PA, efficiency. So it is not only if the steam consists of some dirt is coming, if the steam temperature is varying and exhaust temperature is varying, then, if the alignment level is not good, then it will happen.
Yes.
Otherwise, efficiency will not.
Sir, your point is 100% correct. So steam quality itself is not the only factor, or rather steam quality and the MOC, quality of MOC, what we use is not the only factor. Over a period of 50 years, there will be a natural wear and tear of turbine. So that efficiency drop won't be a huge drop, but still, for sake of theoretical discussion, there will be some sort of drop because of normal wear and tear.
Very nice historical information by Mr. M.K. Vishwas. In 1933, certainly around Bhaveri, they had installed low pressure steam-based power generation, steam turbine. Still, it is working. Nice. This was the last presentation of this technical session. Now, after offering a vote of thanks, after national anthem, we will disperse with the sweet memories.